Okay, welcome back. The next architecture. This is a famous picture. Guys? This is a famous picture. The so-called unit. Why U? Because, well, if you squint, it looks a little bit like a U. Okay. Now, why have the authors arranged it, such? On the one hand, to avoid, well, the picture getting too busy, and on the other hand, you can think of this as we can say that we have a scale here. I don't know if I should draw the arrow up or down. So let's say the spatial scale becomes coarser in this direction. And here, as always, from left to right, I have depth. So if we just look here at this part, it's pretty much the same thing, in principle at least, as we saw in the VGG 16. So we keep decreasing the spatial resolution, we sacrifice spatial resolution, and we increase the number of channels. So we start with an image with a 1 channel or a 3 channel, if it's an RGB image, and down there we already have images which at this point only, so input was 570 by 570, and output is, or at this point we have 30 by 30, and then 1,000, more than 1,000 channels. But this time, the goal is not to make a statement for the whole image. Like, statement for the whole image would be, this was published in a biomedical context. Yeah? A whole image decision would be, I give a picture, let's say, of a histological operation, and the network should decide, does it look like there's cancer or not anywhere on this image, but without highlighting where. But we, or the pathologist, might be interested in, but where in the image is there evidence for cancer? So in this case, we want an output that has spatial resolution. And I mentioned earlier today that this type of problem is also called semantic segmentation. Semantic segmentation means we assign each pixel in an image to one out of a finite number of classes. Now I've given you a medical example. Very popular are these types of examples, very popular in industry at least. This is a picture from the Cityscapes benchmark. The computation itself was from Daniel Kawecki, a master's student, who did this a year or two ago. So on the left we have an input image, and on the right-hand side we have a pixel-wise prediction of, is this road, or is it sidewalk, or is it person, etc., etc. And for people who have worked in computer vision for a longer time, the kind of result which we see on the right-hand side is truly stunning, because people had been working on this kind of problem, for decades, and this is just so much better than anything that was achieved previously. Yeah, so for people who have been working on this for a long time, I think they, well, I did not on that kind of problem, but I think they must be very frustrated that years and years of effort, decades of effort, and then now a student can come and get an architecture from the web and the training data from the web, and then depending on how agile he or she is with computers, this can take 2 days or a few weeks to get that kind of quality result. Yeah? So that's really fantastic. That's a lot of progress has been made clearly. Good. Now, so we want to have an output which has similar spatial resolution as the input, and hence you see that there is what Manuel mentioned earlier. There's now this upscaling, or here in the legend it's called up convolution operation, where from stage to stage the spatial resolution is being increased. Another important feature are these so-called skip links. Yeah? So the perceptron producing an output here sees as input not merely this, but it sees as input also that. And this is indicated by those arrows, these so-called skip links. And so the folklore interpretation of what's happening in this network is that we have up here what's called a geometric pathway. So this transports the information of where exactly. So, and we have down here, we have the semantic pathway, which tells me what. Yeah? So for example, the network decides here in this very low resolution, in this 30 by 30 image, it can decide that, yeah, there's a pedestrian somewhere in this region, I'm pretty sure. But you would like to know where precisely. Yeah? And this information in a 30 by 30 version of this image cannot be transported. So this is why the geometric pathway is also needed to say, all right, the precise outline of this pedestrian is this. And so you want both jointly, the semantic and the geometric pathway. At the same time, you have a finite amount of memory on your GPU. So if you look closely, you will see that where we have high spatial resolution, the number of channels is relatively modest. Yeah? So we have 64 or 128. And in the semantic pathway, where the spatial resolution is low, we can afford many channels and still somehow fit it onto our GPU. So that's a very successful architecture for things like semantic segmentation. All right, and when you can do semantic segmentation, you can do all kinds of things. For example, pose estimation. You will then have something, a network that finds you all the left elbows in the image, and the network finds all the right elbows in the image, and it finds all the heads in the image, and then you get heat maps of where are the elbows and where are the heads and so on. And overall, yeah, if you're lucky, a pretty good pose estimation. So this is a famous video. Let's see if we get an ad. We're lucky, I think. It's famous on the one hand, I think, because the results were really good, and on the other hand, because the music was good. You know, this was 2016. And let's see. And what's cool here is that this is obtained with no tracking whatsoever. Huh? So this is it's being processed independently, frame by frame, and it's pretty impressive to get such stable results. And this is what I wanted to show you. So you have a network that a semantic segmentation network that finds all the places where it thinks there's a left knee, all there's a right knee. And when you have that, you don't have the pose yet, but you know, if you have high quality estimates, it's not so difficult to use a greedy procedure that will then, you know, do something reasonable. So a greedy procedure will collect the parts that cumulatively make up. All right, and this was not precisely done with a UNet, but there's something called a stacked hourglass network in there, which is pretty similar to UNet, in fact. Questions for the UNet? Yeah.
You showed what's done like live on time.
10 frames per second.
Sorry?
Do you mean the pose estimation?
No, they just they have one guy filming the people dancing on the laptop. They just
10 frames per second. Yeah, so near real time. I mean, it wouldn't be a standard laptop. It would be, have a pretty beefy GPU, and the battery would run for 5 minutes. But yeah, a single big GPU. More questions? Yeah.
Where do you get enough pictures with ground truth about posture? But for street view, I mean, I kind of get it that you just get people that are working on autonomous driving vehicles, that they have to go through all these pictures and maybe color in what's a sign, what's a pedestrian, what's a street. But for posture, I mean, that.
Yeah. So
how do you get that much?
So the question was where to get the training data from, and pose is actually it's something of industrial interest. For example, for gaming applications. Yeah. So imagine you are whatever in front of your notebook, or you have a TV and a camera set up. And then the camera looks at the player who does whatever, yeah. And the camera or the game box, whatever it's called, needs to understand, what the human is gesturing. Yeah? So that would be one thing. And then there's, not my favorite application, but people working in this in the context of surveillance, for example, yeah, to find, aberrant behavior, and there are many, many more uses for pose. And so there's industrial interest, and then typically Amazon Mechanical Turk, also known as modern slavery, is being used, and you set up, some browser-based system where you give the workers whatever a cent per 10 annotated images or something, and then you have people, often in third world countries, labeling this patiently. Yeah. Okay. So myself, I work a lot with biological problems, where often, the substrate or the images often change, and so we cannot and also don't want to, each time use Mechanical Turk to generate ground truth. So there's the interesting question of how do you learn from fewer labels, no? And this is very much ongoing research. More questions? Also from you?
Yeah, so we can't there's no methods that involve neural networks with unsupervised learning.
Oh yeah, there is.
How do you do that? So if you don't have any data, or just
well, it's variance of. So broadly speaking, it's variant of data augmentation. Yeah? So, for example, an elegant way of, if you want to train, let's say, an optical flow system or a tracking system, an approach that I thought was elegant was to take a color video and to then turn it into a gray video. And you then, on this gray video, from the first frame on, you estimate optical flow, so where you think pixels go, essentially, or you can try and track pixels or points in the image and see where they're going. And then at the end, you look up, what color did you see at the beginning of the trajectory, and what color did you see at the end of the trajectory. And if you now make certain simplifying assumptions, like the white balance does not drastically change, etc., during the video, then if you've done well, then you will have the similar color because you've correctly tracked the thing. And if you have wrongly tracked, then you get the wrong color. Yeah? So, for example, occlusion is a typical thing. Yeah? Let's say you are tracking my shoes, and they get occluded, and then at some point they appear again. Yeah? And then a good network will have tracked the shoes across the occlusion. A poor network will have, started with the shoes and it got stuck on whatever occluded it, and then you have this color change. Yeah? So that's, for example, a way of having a sort of pseudo ground truth which does not require human labor. Now, the more difficult question is, now from this information, the color was wrong or it was correct, especially how the color was wrong, what should you have done to, where did you go wrong? That's a harder question, yeah? But just to give you an idea, one of these auxiliary tasks that can be given to train a system. All right. I mentioned skip links. I mentioned them in the unit. I mentioned them not yet in the ResNet or real net. What you see here on the left is an element of an architecture called ResNet. So this would be a standard thing, a filter which is 3 by 3 in spatial dimensions. And you learn 64 of them to get 64 channels. Then you have a nonlinearity, a rectifying linear unit. Then you have a linear unit. And then you add to this the output of not the layer before, but the one before that. So you get to see what an earlier layer thought. And now here there is an addition. In principle, you can also do a concatenation, or you can do other operations here. But the bottom line is that there is, when you think about backpropagation, rather than go through all the blocks, there's also a bit of a shortcut to get earlier into the network. And empirically, this helps gradient flow through very deep networks, or empirically, this helps training very deep networks. And before that sort of trick was being used, the performance of deep networks plateaued at 30 layers or so, simply because it was not possible to train them well by backpropagation if the depth was greater than that. And these ResNets can now be trained. This figure is a few years old. But these ResNets can now, they allow you to reliably train networks with many dozens of layers. So that's one important use of skip links. You can carry this idea further and do something which is called a dense net. Here, Becker Huang from the Weinberger lab. So you could say to this convolutional layer, let's not just get the input from the previous layer, but let's get the input from, more previous layers. Now, if you wanted to do that, throughout, you would get super many inputs, and the thing no longer fits into your RAM and so on. So you need to make a compromise between this idea of having dense connections, and on the other hand, still needing a manageable number of parameters. And this dense net is also an architecture that works very well. Okay, so bottom line is these skip links are an important architectural element. Questions? Good. Up next, this is a point I wanted to still get to, even if we don't manage to do everything today. The generative adversarial networks. Who has heard about these before? They are amongst the coolest things to have happened in machine learning in a long while. It is used, given a finite set of samples from some complicated distribution. This is used to learn how to generate more samples from the distribution. And then there are also conditional versions and so on. Here, there are literally thousands of papers on this topic since 2014. I've grabbed a random one just because it makes pretty pictures. It is not a vanilla GAN, but it conditions on things, and there's a lot of engineering that went into this, and I don't want to discuss it. But if we just look at the result, there is, for example, here we have this column source A, and we have this column source B, and then we somehow create mixtures. No? So let's say if we wanted to have a child which has, let's say the hair and skin color and so on of this person, what would it look like? And then the answer is, like that. And similarly, yeah. So if we had there's a teenage girl, but we would want her hair and complexion to be more like that of source A, the result is this. And now you can look at this yourself. And admire these pictures. And source A and source B are real images, at least as far as I know. And all of these generated images here, they're all fails. Huh? These are people who don't exist. And that makes, of course, for all kinds of interesting problems, if you think of the potential of what to do with this sort of technology. And in particular, as these technologies mature, it allows you to sort of live transform you into an avatar, but not an avatar which looks, like a game character, but which, you can, let's say, you can impersonate other people. Yeah? And well, I see plenty of problems there, and I don't think society has, dealt with the problem seriously yet, or has a good answer so far. So it's something I would be happy to discuss towards the end of the semester with you when we talk about ethics of machine learning. But for now, okay, it's pretty impressive. Yeah? So what I've shown you here was the coarse style from source B was used, but you can also take something which they call the middle style or the fine style. And so in the case of the fine style, you would pretty much keep the face, but only try and copy the hair, from source B, etc. All right. So why are people so excited about this? Because I really like I really like well understood mathematical models. I unfortunately have to say that if you look at Markov random fields and such, the kind of images that we could generate easily from Markov random fields, they look like this. And all right, this is now comparing apples with pears. So what I show you on the right-hand side was not meant to look like a face, but it's pretty impressive what kind of complicated distributions generative adversarial networks can sample from. Yeah? And I think this contrast between right and left shows you that images are a particularly complicated class of distribution to sample from. Also, if you remember, what we said about last time about data augmentation. Where was that? Somewhere here. If you remember this example here, point A from the space of all images is a good representative. Point B is also good representative, but the point in between is not a good representative. So this manifold of images that we perceive as natural is a very highly curved manifold and not trivial to learn to sample from. Good. Now, how do they do it? This goes back to Goodfellow. We use a game between a generator and a discriminator. It works as follows. The generator takes as input a random vector. For example, I wanted to sketch here, this is meant to be Gaussian distribution, perhaps, let's say we use a Gaussian distribution in a 128-dimensional space or so, so just 128 random numbers. Then we fit them into this neural network. This would be a convolutional or a deconvolutional neural network. I've written here decoder, and I've sketched it to say it gets few inputs, like 128 numbers maybe, and it produces many outputs. So the output would be perhaps 1 million pixels if it generates an image. So it produces a fake image. If this generator is, before we start training it, of course these fake images will look horrible. Yeah? These fake images will look more or less like, not quite like this, but it gives you an idea. Yeah? So initially this produces horrible images that don't look like images. But on the other hand, we have a collection of real images, of faces, or in one of the standard benchmarks, of bedrooms, or of insides of apartments, or of houses, whatever, real images. And the task of the discriminator is to find out, given an image, to decide, was this a real image or was this a fake image? So the discriminator, and you see I've now again given it a wedge shape to say it gets many inputs, 1 million inputs if it's an image with 1 million pixels, and it produces a single output. One number where 1 means the discriminator thinks it's a real image, and 0 means the discriminator thinks it's a fake image. Now, these two are trained alternatingly. Yeah? So let's say the generator was given some random vector. It produced some fake image, and the discriminator thought, nah, that was clearly not a real image by a long way. But with backprop, we can ask, well, how would I need to change the fake image in order to maybe let the discriminator think it could perhaps be a real image? Yeah, so we propagate gradient from the discriminator to find out what would the fake image need to look like. And from that, we propagate further and ask, well, how do we need to change the parameters of the generator such that it produces a better looking fake image? Okay, this is what I've tried to show here by saying this red connection. I've called this the generator loss, which I should probably extend this red line, because it's not the fake image itself that I want to improve, it's the generator that I want to improve. All right, so let's say we've done this, and the generator has now managed to produce an image which the discriminator actually thinks could be a real image. Now the discriminator can be trained in turn. So the discriminator can be given a real image, or a fake image, and because we know if the image was real or fake, this is a supervised problem. Yeah? So I can train my discriminator to become better at finding out whether it was presented a real image or a fake image. So I've drawn here discriminator loss, and this thing just means heads or tails, where I decide, am I going to give the discriminator a real image or a fake image? All right, and now you train these two alternatingly, and in principle both get better and better. And in principle, at the end, you can just draw samples from this, let's say, Gaussian distribution and get pretty realistic looking images. In principle. In practice, the thing is terribly hard to train. Why? Because, well, these two things, so one problem is because they try to trick each other. The other thing is that, especially in the early stages, the task is often too easy for the discriminator and too hard for the generator. So let's say if we have this space of images, And the space of images, as you know, it's million dimensional, but now I'm making it one dimensional. And in this space of images, we have some distribution of real images. It can be something complicated. It's meant to be a density, so it shouldn't. All right, let's say this is the real images. Then on the other hand, I have this, so this was X. Then on this other hand, I have this space where I can just, simulate random variables. I call them Z here. If it's a Gaussian, well then, this is just a Gaussian in this space. Now the generator maps this Gaussian to some distribution. It maps it maybe to something, whatever. Perhaps before training, maybe this even also looks Gaussian in this space. So this would be G of Z, where Z was sampled according to this Gaussian distribution here. Now the discriminator needs to find a decision boundary in the space of real images, and this discriminator should give a 1 to the real images and a 0 to the fake images. And the discriminator here, it can just solve this problem perfectly. And now my generator, well, it's told by the discriminator, nah, you did a really poor job. Your fakes were just ridiculously bad. I'm totally unimpressed. I, the discriminator, have easily identified them as fake. Yeah? Okay, that's nice and depressing. But if we now look at this decision boundary here, the poor generator does not know how should it change its parameters in order to shift its distribution more towards the real images. Yeah? So you see that this blue curve here, it has no gradient, so it's uninformative. And that reminds you, of course, of when we trained the perceptron in the first place. So what we would like is a discriminator that's not so rude. We would like a discriminator that gives us useful gradient elsewhere. And so a lot of work has been devoted to how to regularize this discriminator, or how to make sure that we get useful gradient even when the discriminator is much stronger than the generator. And one famous paper was on the Wasserstein, which looked at the Earth mover's distance between these distributions. A paper which I wanted to highlight is called spectral normalization. In spectral normalization, you say, I want to regularize my discriminator by not allowing it to have such steep slopes. So I'm bounding what can be the maximum slope of this discriminator in order to get something which gives me more informative gradient, which tells my generator how it should change so as to be able to better confuse the discriminator. And well, this spectral normalization you can achieve by bounding the largest singular value of some of these weights that the perceptrons have. But there are many other ways. The general game is always this. Yeah? Iteratively, given the generator, train the discriminator to give high scores to real images and low scores to fake images, and then vice versa. Given the discriminator, or fixing the discriminator, we want to train the generator to make fake images which obtain as high discriminator scores as possible. And now you can invent some loss function of how do you want to express that. And I've highlighted here in turquoise the loss function that Goodfellow was using, or I highlighted here a simpler loss function that the people from this spectral regularization paper have been using. I wanted to show them these different formulations mainly to say that it's still very much in flux, and even though there may be beautiful arguments for having the logs there. In practice, maybe you get better results without the logs. And I think in essence, what you try and find is a loss function that really implements what I've written here in words. Good. I would like to go on about the problems of GANs and where the community thinks they come from. But time is up, and I'm also not going to go into these other tweaks. You can have a look at them by yourself on how to initialize networks, on how to adjust learning rates, what to do in terms of instead of batch normalization. Next week, we'll move on to probabilistic graphical models, something very cool. And today,